All right, good morning, everyone. We're looking here at a slide that may surprise you as to why we have the standard model of particle physics up. But actually, it is time. See if I can get this thing to go into slides. Okay, I think we're back. It's actually time to introduce and talk a little bit about the other half of the physics behind our model of the Big Bang. And that is the quantum side of things, particularly the modern idea of matter and energy. So we need at least some of the vocabulary of this to continue our discussion and to look at that second level of detail on the model, which is what our objective is today, to take another pass through the model, looking at some of the pieces in a bit more detail. We spent quite a bit of time talking about relativity, which is the other pillar of physics that all this stuff sits on. Special relativity gives us the constant finite speed of light. That allows us to equate distance with time. It's what makes telescopes time machines. And we've talked about E is equal to mc squared, that the equivalence of matter and energy, that they're truly two sides of the same coin. That allows us to make statements like the energy density of the universe is made up of 70% dark energy and 25% dark matter. That sentence would make no sense. The energy density is, but it is the energy matter density, or the matter energy density of the universe, is because of this equivalence of energy and matter that we can make statements like that. In terms of general relativity, we looked at the fact that gravitational fields can bend light, and this is how we can study the distribution and effects of dark matter through gravitational lensing. And we've also talked a little bit about the energy considerations of space-time, and gives us at least an explanation, some kind of an equivalent idea in general relativity for dark energy. And that would be the cosmological constant, one of the concepts that are involved in the fundamental equation of general relativity, connecting space-time with with energy. So relativity has played a big part in underlying and trying to explain some of the big ideas that we have in cosmology. Well, now we need to take a bit more of a detailed look at matter itself. And so that's why this screen is up. It doesn't look like all of a sudden we've changed the subjects, and truly this is clearly particle physics, but we'll need at least some of this vocabulary. Okay. As we look at this, we see kind of two halves. On the left-hand side, in three columns, is the matter of the modern elementary standard model of elementary particles. They're called fermions, and that's the matter that we think of as regular matter. And that's in turn broken up into two pieces. One are called quarks, and the most important for us are the up and down quarks. We'll see that they are the constituents of our good old neutrons and protons. Yeah, you won't see neutrons and protons here. We're not at that level yet. We're at the level underneath that with the truly elementary particles as we understand them today. So the quarks that we're interested in are the up and down quark, which are the constituents of neutrons and protons, and the leptons, the other part of the fermions, and by far the most important there is the electron. The muon and tau particles don't hang around very long, fractions of a second, they're gone, so they play no role in cosmology really. But certainly the bottom row of leptons and neutrinos are always around, and we will be talking about those from time to time. Thought of at one point as a possible candidate for what dark matter is, but it turns out that there's not enough neutrinos to make up for that tremendous 85% of regular matter being this unknown gravitational force agent. Turns out neutrinos won't do the trick there, but they do play a role in our story. It's the right-hand side, which is, of course, so new to us, something that we did not grow up with in our high school chemistry classes. And these particles are called bosons, and they're the gluons, photons, and the Z and W bosons, and then as of 2012, finally the discovery of the Higgs boson. These are particles, but notice I put the word fields in parentheses. These are particles that come from force fields. The gluon comes from, let me bring this up, comes from the strong force, which is what keeps the quarks together to allow the creation and stability of protons and neutrons. There's the photon, which we're more comfortable with as an idea, as a particle of light, but they are actually the force particles of the electromagnetic force. And the Z and W bosons are responsible for the interactions for the weak force, mostly as it's described as responsible for the radioactive reactions that we see, neutron capture, neutron disintegration, and alpha particle and beta particle disintegration of radioactive nuclei. These are all involve the interactions of the Z and W bosons. And then finally, there's the Higgs boson, which is the last one to be discovered. And this is attributed to reason why all the other particles have mass. Clearly, this is an entire subject in itself. This is more than a whole course in itself, but I just wanted to give this slide so at least we have a reference to some of the vocabulary that we'll be talking about as we go forward. And here I've isolated the two quarks that are of most importance to us, the up and down quark. And as you can see, I kind of make a little division here. It's the proton is made up of two up and one down quarks, and the neutron is two down quarks and one up quark. The other essential elementary particle is the electron. And all together, we'll see on the right how that's put together with our more familiar chemistry that we grew up with. Having protons and neutrons as part of the nucleus, making up the nucleus, and then surrounding that nucleus with electrons, we finally get our stable atoms. And those numbers on the left and right are interesting to show the sizes, the relative sizes of things. And always one of the most interesting is the first one going down from the top, saying that the atom is in fact much, much larger than the nucleus. One of the great discoveries done by Rutherford in his famous gold leaf experiments to see how tiny and how in fact heavy all of the mass of an atom is in the nucleus, as tiny as it is, just 1/100th of the entire radius of the atom. So this will kind of at least remind us of some of the vocabulary that we'll be using as we talk about matter in this way. One more vocabulary word, if I could. The protons and neutrons are often just called nucleons. That kind of is pretty natural for us because they live in the nucleus, they make up the nucleus, but they're also called baryons, and we'll see that word as we go forward. And all baryons really are in general, the official definition of baryons is anything which is made up of quarks. But to us, by far, the most important baryons are good old protons and neutrons. The other baryons, like I say, don't really last very long. They're created in particle accelerators and they're gone in a blink of an eye. They don't have much of a role to play in cosmology. Okay, so let's run through at a high level just what the Big Bang model is in its different stages, and then we'll go to the second presentation, the new presentation for today, where we'll look at some of these pieces in a bit more detail. That's the game plan. So really where we ended last week was a very natural place, because here we are ready to kind of look at the lambda cold dark matter model of the Big Bang in its various different pieces. So the conventional story is the Big Bang starts at time is equal to 0, whatever that means, with an infinite temperature and a 0 volume. All these things make no physical sense to us. So the physicists give it a word. It's called a singularity. Don't know if that helps at all. Um, but the first meaningful, according to quantum theory, the first meaningful tick of time is a ridiculously tiny number of 10 to the minus 43 seconds. That's called a Planck time. It has one of those pretty equations. The Planck time is the square root of h capital G over 2 pi c to the fifth. It is a very pretty formula. Of course, we can't explain it. Imagine the theory behind a formula like this, but we do recognize the pieces. H is Planck's constant, G is gravitational constant, pi, of course, is pi, and c is the speed of light. So there it is. Where the theory, how the theory puts these ideas together for the mathematics to speak to such a pretty formula like that is one of the great mysteries of the universe, for sure. How mathematics can describe these things and in such a beautiful way. But it's here in the first time, the first possible time that we can even talk about is where it's thought that the gravity force differentiates itself from one point all the forces were all together, but gravity breaks itself off first as a separate force. I guess we need that because without gravity, there's no such thing as space-time. There's no general relativity. There's nothing to talk about. So yes, it would make sense that gravity would have to have its independence so that we have the whole notion of space and time as we understand it. Then we get some first duration of time from 10 to the minus 43 seconds to the 10 to the minus 36 seconds. This is just totally ridiculous in terms of a true duration of time. But here, again, an important event is thought to happen. This is where the universe is this tiny, tiny thing, as small as you want to think of, smaller than a proton, as small as you would like to imagine. And all the universe is at this point is just quantum fluctuations of energy. Well, again, that's kind of like saying the sky is blue. Well, what else would there be? If all you have basically is space-time, and now we have the emergence of the laws of quantum physics as we understand it, according to Heisenberg's uncertainty principle, in a tiny, tiny volume like that, in a tiny, tiny time frame like that, all that you could possibly have are fluctuations of energy. It's the only thing that the theory allows. So yes, okay. So we assume that that's what we have, thinking that the laws of quantum physics begin at least to take over. Another important event that happens during this tiny, tiny time frame is that the strong force now breaks off from the other three, the weak force and the electromagnetic force. And that is thought to be the trigger for this next event, maybe in a sense the most important of them all in this slide here is the period of inflation. So again, this is all very speculative stuff. There are scientists who believe that this is our best explanation. There are other cosmologists which are not at all convinced, still looking for a better explanation. That's more the topic for our last class. But going through the conventional story, it would be the strong force that breaks off at this point, and it would be in some way the trigger for the next event. And you see, the next event at least happens for a little bit of time, from 10 to the minus 36 seconds to the 10 to minus 33 seconds. Wow, what a big deal. And you can see the temperature drops quite a bit here, from 10 to the 27th down to the 10 to the 22nd. That's a 100,000 time cooling effect during this period of inflation. And inflation is this incredible event where the size of the universe expands up in a ununderstandable way in terms of just the scope of its size. Here I've written down to a factor of 10 to the 50th. By the time it ends, it's 10 to the 50th, bigger than it was when it started. I've seen numbers as low as 10 to the 25. I've seen numbers as big as 10 to the 76. Where 76 comes from, I don't know. So it's, again, this is controversial stuff, and the physics is not as well understood at these temperatures and these time frames to make hard and fast predictions. That's just the state of our knowledge right now. But during this time frame of this incredible expansion of space-time, and therefore the expansion of these quantum fluctuations, we'll be coming back to that again and again. These original quantum fluctuations are blown up to become the universe of some kind of a decent size. Some people call it the size of a grapefruit. Some people call it the size of our solar system. I've seen things, those two extremes and everything in between, just because of the uncertainty of all of this. It's here where the weak force differentiates itself from the electromagnetic force. And we do have then at the end of the inflation period, a place where we think we understand the laws of physics. Basically being the laws of quantum theory and general relativity. That's the hope of how this model can continue. Remember those very fundamental assumptions that we're making so that this model can at least be laid out. Assumptions may not be right, but we lay them out this way so at least we can tell our story. At least we can try to do some physics. We can try to make some predictions. We can try to test those predictions. We can try to see if our story can be substantiated by evidence. That's all science can do. When the evidence does not bore out the predictions, you go back to the drawing board and you try to find other assumptions. So after this incredible period of inflation, we have, wow, what a long time frame. We go down to a microsecond, 10 to the minus 6 seconds. We go down all the way to as long a time frame as a microsecond. And this is where matter and antimatter are formed. Where does it come from? It comes from the residual energy of the inflation. This inflation clearly is an incredible amount of energy to expand space-time like this. Where does the energy dissipate to? It is thought that the energy dissipates into the creation of matter and antimatter. Now we're beginning to get on more solid ground of the physics that we know. Energy can produce just matter, yes, and we'll see that. Okay, we'll see how that has been demonstrated in our laboratories. So here, the period of inflation is thought to have done this on a grand scale, besides differentiating now all the four forces of the four boson particles, which can now intermediate the fields of these forces. So we have matter, we have antimatter, we have radiation as we understand it, we have the photons as we understand it, we have the formation of dark matter as we don't understand it. But if you're going to create matter, you might as well create all of it. Since we have no idea what dark matter is, we might as well throw it in here. Where else you going to put it? We have, it comes along for the ride. Why wouldn't it? If it's there in some form, which is what our assumption in our model is, it's created during this time frame. And so in terms of regular matter, we have this plasma of photons, quarks, and no neutrons and protons yet. The plasma is of quarks and neutrinos and their antiparticles. A very strange plasma. This is a plasma which is not very well understood. This is a plasma which we can't create very well in the lab. We certainly can't create a mass of this stuff. You can't create a mass of quarks. Never mind antiquarks. Never mind having them last more than a microsecond or even less to study them. A plasma like this is not very well understood. But if we're going to get to the plasma that we do understand, logically, we have to start with this guy. We have to start with this plasma, which will melt into, if you like, the plasma that we do. And that's what happens finally with a time frame that we finally, can think about, right? From a microsecond up to a second. And notice again the tremendous drop in temperature down to 10 to the 13th, right? Which will be 10 trillion degrees Kelvin. That's 10 trillion degrees Kelvin. That's much, much hotter than the interior of any star. But here is where the quarks can merge finally into protons and neutrons. The strong force can finally bring together these quarks. They're not moving so fast now. They're not jumping around so crazy way that the strong force can actually grab them and hold them together. And here is where we see the beginning of the nuclei as we understand it. Not nuclei yet, They're still separate protons and neutrons, but at least they begin to form, and the quarks disappear as loose particles. They all become locked in by the tremendous power of the strong force into protons and neutrons. We're starting to get into matter that we understand. Electrons and positrons are also created here. The positron is the antiparticle of the electron, the first antiparticle ever discovered, first predicted by Dirac in the 30s and then discovered in the early 50s. And here is where something quite extraordinary happens, is that it's called baryogenesis. We love to give things names that we don't understand. Oh, it's got a name anyway. That's a start. It's kind of like the caloric when we didn't understand what heat was, or the ether when we didn't understand what the fifth element that was pervading all the universe for Aristotle. We love to give things names when we don't really understand them. And so baryogenesis is the period of time, the event, the process in which somehow or other the ordinary matter, and there was an excess of ordinary matter over antimatter. We know that matter and antimatter annihilate each other when they come together, giving off pure energy. That happens, but since there was an excess of ordinary matter, when the war was over, some ordinary matter was left. Better be, otherwise we wouldn't be here talking about it. So this had to have happened. We have no idea why, and we give it a name, baryogenesis, tremendous area of research of what could have caused this disparity in the creation of matter and antimatter. Because when we create matter and antimatter in the lab, in the great labs of the world, like in CERN and in Fermilab, we always create them in pairs. So we don't know how an imbalance could have come about, because we only know how to create them in pairs. Our physics tells us they're always created in pairs. So how is this imbalance to happen? It's one of the great unsolved problems in all of modern physics, what this baryogenesis is. But to help us, our plasma now changes to protons and neutrons and photons and electrons and neutrinos. This is a plasma that we can study and have studied. And this is pretty much where Gamow and Alphers, his graduate student, started their study of the Big Bang. This is what Lemaitre had in mind of the cosmic egg. This was at least a form of matter that they understood. Could be very, very hot, obviously, 10 to the 13 degrees Kelvin. Could be very, very tiny as you want to make it. But at least it was made up of matter that they understood, even in the 40s, even though maybe that could have been studied in detail in the lab. So this is where the Big Bang theory actually started. That's important, guys, to remember how this theory actually developed historically. It actually begins here, at this point in the story. And it has moved in both directions as our understandings become greater and greater. It has moved down, okay, to what happens to the plasma as it expands and cools. That is more and more known physics, and more known as we went into the 50s and the 60s, and then making that incredible prediction of the cosmic microwave background. And also, very importantly, to move up this scale to where we've just come from. That little by little, trying to understand more and more physics, finally getting to understanding of the standard model of particle physics, to start to talk about these kinds of things, the separation of the bosons, where all the bosons at one point were one kind of boson, where all the forces were one kind of force. All this had to come from the 60s and the 70s, where this theory, people would go back, the physicists would go back to the Big Bang theory and try to fill in more of the holes. And this is how the theory actually has developed historically. It's a very, very interesting story in itself. And what it shows is, one of the interesting things that it shows among many, is how particle physics, how the quantum world began to marry with cosmology. And they helped each other, because although you can't create these kind of environments, these kind of temperatures in the lab, it was thought that these temperatures did exist at some point in the evolution of the universe. So can we study that part of the evolution of the universe? Can we see any evidence of that now? Can we look now and see evidence of when the universe was that hot and had those kinds of matter as its constituents? If we can study evidence of that, then that would be kind of our virtual collider, our virtual accelerator to study this. And there's been an incredible symbiosis between particle physics and cosmology, something which was not even thought of in, for example, Hubble's day, when he was showing how all the galaxies were moving away from each other. It was just not thought that this would, could have such a fruitful marriage of ideas. And it's really one of the great stories of modern physical science, of how these two extremes of the study of the universe, the very, very small and the very, very large, have actually contributed to our understanding of each. And finally, we get the famous number of 380,000 years. That's a number we should say, oh yeah, I know that number, right? That's when the cosmic microwave background is released. But up until that time, from about 1,000 seconds, about 16 minutes to 380,000 years, is finally when the nucleons are made. This is when the nuclei of hydrogen, which is simply just the protons, they haven't changed much, but this is where we have the creation of helium. In the world of radioactivity, they're called alpha particles. They are 2 protons and 2 neutrons. And finally, the temperature has dropped low enough where they can stabilize and they won't be torn apart. That the strong force is strong enough to hold the quarks together, and the and the force of the protons and neutrons together, where they will not be broken apart. And we have, like I say, a plasma that we can study. Okay, just a picture of that breakup of the bosons of the forces, starting with the breakup of the gravitational force. You have the bomb that breaks up first, maybe being a spark, breaking up of the strong force, and then finally the breakup of the weak force, and having all 4 forces separated together. And you can see the incredible tiny time frames when this is happening. Okay, and just to finish the high-level view, we get to recombination and decoupling. We've talked about this many, many times, where we finally do have stable atoms, where the electrons can now stay with the nuclei. They won't be ripped away. And when those electrons are finally captured by the nuclei, it allows the photons to move freely. And that is the cosmic microwave background. We then have this interesting period of the first couple of million years, where the cosmic microwave background goes from 3,000 degrees, where it has this deep red glow, getting colder and colder as the universe stretches, to finally fall into the infrared. And there is no visible light, at least to our eyes. And that period lasts for many millions of years, hundreds of millions of years, called the Dark Ages. But there are things going on. We can't forget dark matter. Dark matter, remember, is not affected by the radiation. And although the radiation, being very strong, did not allow the regular atoms to start to coalesce, they were still more and more a diffuse gas. The gas was just getting cooler and more diffuse. There was no clumping going on at all of the atoms that we know and love. But the dark matter is not affected by the radiation, right? The dark matter only seems to be affected by itself. And the only effect it has on itself is gravity. And so the dark matter could begin to clump even as early as this. And certainly as we get into the Dark Ages, talking about 100 million years, 200 million years, etc., this is where the actual structures are thought of the earliest structures, which would be dark matter structures, begin to form. And this is where people can start to think about creating those simulations that we've studied of the structure, which ultimately will come into the voids and filaments of the galaxies and superclusters, etc. Finally, this regular gas will begin to clump together, maybe with the help of dark matter surrounding it. Again, this is one of the most vigorous parts of the research of astronomy today, of the beginning of the early stars and galaxies. But ultimately, fusion does begin. The hydrogen does fuse into the great stars that we can understand. And then those structures will continue to grow and become what we can recognize as galaxies, et cetera, et cetera. 8.8 billion years after the Big Bang is when that acceleration that was learned of in 1998 seems to kick off, is where dark energy begins to dominate over the matter, which is mostly dark matter. And that's why it is thought that the cosmological constant in the equation of general relativity dominates, and we get the beginning of not only the acceleration. Universe was always accelerating, always, never contracted. We have no evidence at all over the 13.7 billion years that the universe ever went into a contraction, but it's the different rates of expansion that we're talking about. And it's the dark energy here that begins to kick in, where the acceleration begins to, the expansion begins to accelerate. Okay. So if I had showed you this picture at first, it'd be completely overwhelming. You wouldn't know where to look first. But if you just take a look at this in a minute, and this ends our presentation, we want to get on to the second presentation. You look just at the left-hand side. You recognize all these things. There's the quantum fluctuations. Look at the left-hand side. The electroweak, this is where the electroweak forces are still together and they'll break up. There's baryogenesis. There's nucleosynthesis. There's the era of the nuclei. Okay, there's the cosmic microwave background. Okay, the development of normal matter and the fusion together, the first stars, the first galaxies. On the right-hand side, not so bad. We've got the inflation era. We've got the strong force separating, the electromagnetic force separating. We've got matter and antimatter creating and annihilating each other. We've got the creation of normal nuclei, 75% hydrogen, 25% helium. We've got the plasma forming that we understand it, plasma of hydrogen and helium nuclei, plus the loose electrons. Then we have the cosmic microwave background. 400 million years is the first stars, and then we get the galaxies. So yeah, we know all these pieces, but when you want to, if I showed you this whole thing together, you know, it would be just look like chaos. But hopefully this is not so chaotic looking now. It's an attempt by somebody to try to put all this together on one piece of paper. Not so easy. All right. Okay, Greg, do we have any questions while we're switching screens here?
Yes, Peter, we have one question from Joe Parisi. What are current theories on what initiated the Big Bang?
We'll be talking about that, Joe, in this presentation. You asked. Thank you, Joe, for that question. That's all I can say. It is the perfect lead-in to this presentation because we will see so much of our focus will be on the early part of the creation story, the Big Bang story, and the heart of that is very much in inflation. So this is the picture. This was the one picture I asked you if you could think about one picture, not the last picture I showed you, but if you did have one picture in your mind of the model of the Big Bang theory, this is not a bad one. And I break this up into three stages in our presentation here, where the first focus is going to be to bring us up to the cosmic microwave background, the release of that. This is bring us up to recombination and decoupling. The second stage takes us through the creation of the expansion of that plasma the expansion of the atoms and starting the fusion process, starting the clumping process of first dark matter and then regular matter, and finally getting into the first stars and the first galaxies. This is a very, very important part of modern research right now today, is to try to understand this stage. And then the third stage would be, you know, the modern stage. I just asked you to notice that this is not divided up in time properly, right? This is okay. If you look at the ages here, guys, realize that we're going from 0 to 380,000. Then from 380,000, we're going to 1 billion. Okay, that middle piece is millions of times bigger than the first piece in terms of length of duration. And the last stage is, well, 13 times bigger than the first two stages put together, right? From 1 billion to 13 or 14 billion. So this is not to scale in terms of time. it's trying to fit in, all the important pieces. Greg, before I continue, was there another question?
No, there are no more questions.
Okay, you guys are great. You're letting me move on. You can see I want to try to finish this today. My goal, guys, is to finish this as much as I can so that the presentation next Friday will be relatively short. I'll try to outline some of the problems and open questions and controversies of our model, alternatives. I'll have some videos for you guys to watch beforehand. And I like to open up as much as I can of the last class for an open mic and questions and discussions. I really respect what, you guys, what you think, the questions that you have, the considerations that you have, and I'd love to make some time next week for that. So I am trying to move along here to finish just the presentation itself. Okay, so focusing on that stage one, begins with quantum fluctuations. What else do you have? That's all you got. The gravitational force separates, the strong force separates. We have the important era of inflation. That leads to the creation of matter and antimatter and radiation as we understand it. Remember, the quantum fluctuations don't have necessarily radiation as we understand it. It's just, I don't know, it's just quantum energy. It doesn't get differentiated until the forces get differentiated. But we do finally begin to have the beginning of matter as we understand it, fitting into the standard model. Remember, this matter creates matter and antimatter, the quarks, the electrons, the neutrinos, and the dark matter. Baryogenesis, where the excess matter somehow or other annihilates the antimatter. Well, the annihilation is not a strange thing, it's the excess. That's why I put that word in red. The excess matter, where's the excess matter come from? Not known, not understood. We move from baryogenesis to the creation of protons and neutrons, and then from protons and neutrons, finally, we get to nucleosynthesis, something that I want to take a look at. I want to spend a few minutes looking at this. This is what Gamow and his team were trying to understand back in the 40s and early 50s. This is one of the great successes of this model. And it truly shows the incredible kind of successful crossroads between cosmology and nuclear physics. We move from there to the plasma, and the plasma lasts, this plasma of nuclei and electrons and photons. Very interesting to realize that this plasma, is very special here before the cosmic microwave background is released. This is modeled as a gas, but it's a very interesting gas. It's a gas not only of matter, of nuclei and electrons, we get that, but it is so hot, the electrons are moving so quickly that they don't allow the photons to move through it, that the photons are continually being stopped. Their mean standard distance of travel is tiny, to use the official word of the statistical analysis. This again is a very special plasma that we can't recreate in the lab very easily. We can only get hints of it, that the photons are actually acting like the nuclei and the electrons in all one crazy gas of these different species of matter and energy. It's a fascinating idea of this expanding plasma before the recombination and decoupling, before the release finally of those protons, of those photons, the release of the energy, where finally in that cooling process, we can get to a plasma, still very much a plasma, but at least we can understand it, and it begins to cool very rapidly, and the atoms form. So again, the plasma here that we're talking about is hydrogen, H+, deuterium, which is a hydrogen, which is a proton and a neutron, helium, 2 protons and 2 neutrons, and lithium, 3 protons and 4 neutrons. This is the stable, unradioactive lithium, small traces of that, electrons and neutrinos. Okay? This is the plasma that we're concerned about, the plasma that we can study. We don't really have a role for dark matter in this plasma, not that it's not there, but since it doesn't interact it doesn't seem to interact with the matter, and certainly not with the photons in any way. And it doesn't seem to interact with the other matter pieces except by gravity. And there's so much more dark matter than of this stuff, 5 times more, according to our model, that we can ignore that the behavior of that except for the clumping and leave this to be studied as conventional physics, that it'll ignore what the dark matter is doing except on the level of gravity, which is creating, the lumping. The idea is as soon as the photons dissipate enough to allow matter to begin to function without the bombardment of this incredible high radiation, which very much affects matter, the photons, the pressure of the light pressure of the photons. Once that dissipates, then we can start to think about this kind of matter beginning to clump. The dark matter started earlier. Okay, and we come to recombination and decoupling. So take a look at this graph. This idea of inflation is actually quite extraordinary. The old theory of the Big Bang is shown in that red line of the expansion. Started much bigger, kind of the nuclear egg, Lemaitre's egg was kind of a little bit bigger, in the sense 10 to the minus 10 meters. Okay, that's big. And the expansion was kind of stable, going up to where we are today. This has some major problems, which we'll go into in a moment. I just want you to look at the difference of what the inflationary model does. Okay, this model this idea of inflation. Remember, was done by first presented by Alan Guth in 1979. 1979. That's why we didn't learn about it in high school. Okay, this is a very, very new idea, and it had a tremendous run for a long, long time. But now in 2020, there's lots of doubts to it, and that's what we'll get to next week. But if we were doing this course 20 years ago, in 2000, or even a little bit before, inflation was pretty much accepted by 99% of the cosmologists and physicists, of the world. Only now, as we've gone to learn more and more and more, and the more we learn, the more questions come up, and the more we can ask intelligent questions and look at intelligent alternatives. It's called science. I'm sorry, guys, but after I've been listening to, this is what science is. Okay, end of commercial. So we want to look at why this was presented, why this new idea was presented. What would motivate this crazy idea? It really is a crazy idea from a layman's point of view, where we start the universe at such a small place here, and the rate of expansion is, you couldn't even call it exponential. It's well, it is. It actually is exponential, but it's off the charts exponential. Why would you need this kind of a situation? What are we solving here that this doesn't work? This kind of a normal natural expansion doesn't work. And so let's spend just a couple of moments looking at 2 of the 3 major problems. The third problem is a little wonky, and we don't really need to go into it. But these 2 problems are understandable, and it really shows how the inflation does solve it. One is called the horizon problem, sometimes called the smoothness problem. Problem is this: we find that the universe at its largest scale is homogeneous and isotropic, right? No matter which direction you look at, it always you're looking at the same expansion in any direction. That's isotropic. It's homogeneous. No matter where we plunk yourself down in the universe and you look around, it's the same as any other place. There's no special place. Why is that? Remember, the universe is supposed to start with quantum fluctuations. Quantum fluctuations are not homogeneous and isotropic by definition. Quantum theory does not allow this. Also, the temperature is so even. The temperature we know it finally evolves into the temperature of the CMB. The CMB's temperature is incredibly smooth. It's 2.7 degrees to 2 decimal places. It doesn't change. You have to go out to the 3rd and 4th and 5th. Actually, have to go out to the 4th decimal place, to the 10,000th of a degree, to see a change in temperature. Quantum fluctuations don't allow this. How did it get this way? How did it get so smooth? Well, inflation does explain this. It explains it in the following way. You can't get this evenness of temperature if not at some point all the area, all the volume of the universe at one point was in what's called thermal contact. Reason why the spoon in the coffee, the hot coffee gets hot, is eventually the heat of the coffee will go into the metal of the spoon and we'll get one common temperature. The coffee should cool down a little bit and the spoon should heat up a little bit, and you come to thermal equilibrium. You don't get that unless the spoon goes into the coffee. You can't get this kind of CMB even temperature unless the universe was all in thermal contact at one time. That original slow expansion doesn't allow for that. Okay, and the areas were so spread out in the beginning. Speed of light is not fast enough to move through it to have everyone in thermal contact, and you shouldn't have this kind of even temperature. Not with that kind of expansion. There would not be enough thermal contact throughout the entire region of space-time. Okay, so the theory of inflation makes the universe much, much smaller, and therefore everyone can be in thermal contact, and therefore we can get thermal equilibrium before this expansion starts. Okay, and then when the expansion starts from this tiny, tiny area, the smoothness is there, and it'll continue to be there. You realize all these words are turned into equations. This is all, semi-understood science. Well, that's what they're struggling to understand, trying to understand deeper and deeper questions of quantum theory to try to justify this, what I just said, in very, very high level words. Understand there's tremendous science behind this, computations behind this. We just have no ability to go through that. So we stay on this, on this level here that we can understand. So inflation solves the horizon problem, as it's called, because the entire universe at one time was in thermal contact, and the expansion continued that, did not break that thermal contact. The other problem is called the flatness problem, and that's even easier to understand. Why is the universe flat? Why is that geometry flat? And we'll mention this again, what we exactly mean by this when we get to the evidence for it. Hold on that. The related question is why is the matter energy of the universe so incredibly close to the critical density? Right? Why is it within 1%? The measured number is 1% of the computed number. That sounds like an incredible coincidence. How did it get to be this where the measured matter energy density is virtually on with the critical density? Well, that's because the geometry is flat. The only reason why the geometry can be flat is because the matter energy density of the universe has got to be at the critical value. Okay, and it is measured to be so. But we know theoretically it must be so because we know that the geometry of the universe is flat. How did it get this way? Quantum fluctuations don't give you a flat geometry. My God, the exact opposite. Space-time would be bulging up and down, energy coming in and out. The warping would be beyond belief. How does it come to be flat? How does the CMB, which is the result of this evolution, come to be so flat? Well, the picture's down below. I picked one where I wanted to emphasize again the horizon problem. It does solve the horizon problem with the, the small universe starting with. But here's the flatness. Okay, literally, it's this simple conceptually. The equations don't even say all that much profoundly. That if you take this tiny ball and you expand it up by 10 to the 50th, well, that just will flatten everything out. Right? The sphere will become so large that it is virtually flat. That's what the inflation does. It's a very simple idea to understand. I'll just say one word about the history, again, the history of the development of the theory of inflation. It's very interesting. The third wonky reason that Booth was worrying about where he came up with the idea of inflation. Once he thought that inflation solved his wonky idea. By the way, the wonky idea is called where are the monopoles? You can Google it if you want. If you guys are serious about this, please go ahead and Google the original problems of inflation. You'll read all about the missing monopoles. This is what got him to give the idea of inflation. And then he quickly realized, wow, but this solves the flatness problem and the horizon problem. I've really got something here. This could be important. And he went from an obscure postdoc particle physicist to one of the most famous physicists in the world. So, what caused inflation? Oh yeah, guys, I don't know. I gave you a video to watch, which is more detailed discussion of this. This is what I kind of picked out, what I could say at a high level. This is the energy density curve that embodies the field. It's called a scalar field. It's called a false vacuum of energy. And the ball rolling down the energy curve is analogous to math, is very similar to a ball rolling down a hill as it loses potential energy and gains kinetic energy. This is the process of the expansion of inflation, is what the ball is representing. And what's important here is that the plateau is much longer than a regular fall, in a sense, that the ball stays at a constant speed, that the density stays at a constant amount for a long time in this field. And this is what drives the expansion, because it's not losing energy density. It's creating all this new energy, but it's creating this energy in a bigger and bigger space-time. So the density is staying the same. The energy over the volume of space-time is staying the same. Well, this expansion is making the volume bigger and bigger. Therefore, the energy must be bigger and bigger in order for the density to stay more or less constant for a long period of time. Scalar fields, false vacuums, these are all complex, advanced notions of quantum physics. There's no way for us. We can just give these things names. You can read, there are physicists much more knowledgeable than me who make an attempt to explain this. I gave you one 13-minute video of a very well thought of series where he tries to give an explanation of this mechanism of inflation. It's the best theory. It's not even the only theory of what propelled inflation. That's how controversial inflation is, but it's the best theory that we have. It's the one that, if you're going to believe in inflation, it's the one that most physicists will ascribe to, even though we all recognize there's lots of unknowns about it, dealing with at the forefront of quantum theory. What's important is at the end, where does all this energy go? Well, it has a good place to go. It goes into us. It goes into the creation of the matter and the antimatter and the dark matter, which could have antimatter, who knows? Baryogenesis could have also solved the antimatter of the dark matter problem. If in fact, dark matter is matter, it's an open question. Maybe it's not, it has gravity, but maybe there's something, et cetera, the unknowns. So that's the best I can do to ask what caused this incredible event. It's not known, okay? It's not settled. All right. So talking about the creation of this matter, we go from these quarks to the protons and neutrons, okay? To recognize this, and the dark matter is created. As the universe expands and cools, as we say, the strong force finally has the ability to, first of all, capture the quarks in protons and neutrons, and then actually capture the protons and neutrons. Yeah, same force, strong force, same force, can capture the protons and neutrons into nuclei. Most important being deuterium, which is one proton and one neutron, a isotope of hydrogen, and the helium nuclei. Okay, baryogenesis. What can we say about this incredible unknown? As I said, in the lab, all that's really known about how to create, and we can create matter out of energy. Here's an example. This was done in the 50s. Take two protons and accelerate them to a tremendous high kinetic energy. Set them moving at each other at the speed of light, where the two protons are there and they have this incredible amount of kinetic energy. You can create a proton and an antiproton. All of a sudden, you'll have the two protons and another proton and an antiproton. It comes out of the pure energy of the kinetic energy of the motion of the two protons. We've done this. We've done this in the 50s. People have won, the Nobel Prize in 1959 was awarded for this experiment, okay? But they're always created in pairs, right? So how the excess of matter came to be, we don't understand. One of the great problems. So we give it a name and we leave it to the experimentalists and the theorists to keep looking at the problem, and we move on. We move on to nucleosynthesis. Okay, now now the temperature is cool enough where we can have all kinds of interactions that we understand. Okay, and you can see the long list on the right. The only thing I should point out is what really is needed on those equations. On the left-hand side of the arrow, you should have plus energy. There's a neutron and a proton plus energy will give you a deuterium and gamma rays. Okay? A deuterium and a neutron will create helium-3. Hydrogen-3, another isotope of hydrogen, an unstable radioactive isotope, plus gamma rays. So we need energy to create these kind of reactions, but God knows there's plenty of energy at this point in the plasma that we're talking about. This will not last very long. Interestingly enough, this only lasts for 17 minutes. I know it sounds crazy, but this is actually quite known physics. We're now in the area of known physics. And the temperature will drop to a point in 17 minutes where these reactions can no longer happen. There's not enough energy on the left-hand side of the arrow to create the right-hand side. They've got 17 minutes to create this stuff. And there's a limited amount of stuff that's created, interestingly enough, as we'll see. All right. So I can see that we only have 15 minutes left, but this, I think, is not only very important, but very interesting. I'd like to take us through this. This may take us, the rest of the class, but I think it's worth looking at, to look at the process of nucleosynthesis. Where did the hydrogen and the helium come from, and traces of lithium? It's in that picture on the left. But before we look at the picture, up on top, you have to realize that scientists can make a computation using quantum theory to see that plasma will settle down to a ratio of 7:1 protons to neutrons. And we can't go into the explanation. It's because of the nature of the weak force, which is creating these reactions like the one up above, where a neutron will become a proton and an electron, give off a neutrino, and vice versa. Protons and electrons can be banged together at the proper energy and create a neutron. This synthesis goes back and forth. This reaches an equilibrium of 7:1 ratio of protons to neutrons. We'll have to accept this as known quantum physics. So we start with that ratio of 7:1. And here's the picture. We have a neutron and a proton. They come together. They create a deuterium atom, deuterium nuclei. So there are no atoms here. A deuterium nuclei of a proton and a neutron together. This happens twice. We get two deuterium nuclei. They bang together between this tremendous energy that's going on. They're all moving at an incredible high kinetic energy. All that is just temperature. That's all temperature is the measure of the kinetic energy of the particles. Okay, temperature is not some mysterious thing. It's the motion of matter. So these two high energy deuterium atoms bang together and create a helium-3 nucleus and throw off a neutron. This is known physics. We do this in Fermilab all day long. Okay, and finally a helium-3 will bang together with another deuterium nuclei, plenty of them around, and will create the stable helium, okay, and throw off a proton. Notice what we've thrown off in this process. We've thrown off a neutron and a proton, just what we started with. So this process can continue and continue, okay? And if you remember from our chemistry class back in high school, every reaction, atomic reaction, and even these nuclear reactions, you have to have a balanced equation. And this is the balanced equation. If you start off with 14 protons and 2 neutrons, you will wind up with 12 protons. Now we call them helium nuclei, hydrogen nuclei, and 1 helium nuclei. And they balance. 14 plus 2 is 16, and 12 plus 4 is 16, okay? And this is the chart. I won't go through this chart, but it is a lot of fun. Go through each of these pictures, one by one, of the bangs, and check out what you have in terms of protons, neutrons, deuterium, helium, helium-3, and helium. And all the numbers continue to work out. You continue to have 16 nucleons at all stages and a charge of plus 14. It never changes. Every single reaction is balanced. And what you wind up with at the very end is you went from 14 protons down to 12, and you went from 2 neutrons down to none, no deuteriums down to none, no helium 3 to start with, no helium when you finish, and you wind up with a helium nuclei. And every single stage is balanced. It's very cool if you want to look at that. And now the computation. Well, how much helium was made? By mass, we'll take the 1 helium nuclei over the 12 hydrogen nuclei, protons plus the helium. What's the ratio? 4 over 16 is 1/4. So we should see in the primordial gas, in the voids, which is where the stuff is still there, unmolested by anybody, we should see 25% by mass helium and 75% hydrogen. And that's what we see. That's what we see in the spectroscopic analysis of the gas, the cool diffuse gas of the voids. This is one of the strongest pieces of evidence for the whole Big Bang model. This is a big one, and that's why I wanted to spend some time on it. And this graph is just great. Take a deep breath. This is really interesting. Let me walk you through this. This is not all that complicated, okay? There's just a lot of different species of elements all in one graph. That's all why it's so busy. This is the fraction of matter that there is, okay? And notice that these are in 10 to the minus 2. This is a 100th of the total mass. This is a 10,000th of the total mass. This is a millionth of these are very, very small fractions as you go down. And this is time in seconds. This is 10 seconds. Okay, this is 100 seconds, better known as 2 minutes. And here's our 1,000 seconds. Okay, and what happens is the temperature, which is finally down here, drops to a point where the reactions simply stop. Okay, the red line up here is the protons. Protons don't change virtually at all. Okay, some of the protons, yes, do go into helium. Yes, they do. Okay, but by and large, the vast majority of the protons stay. They go from a ratio of 14 to a ratio of 12. Look at the helium. Look at the dotted green. The helium starts at nothing. Okay, but as the deuterium is created, as more and more deuterium is created, we know that that reaction can create the helium. And so they come up together. They come up, and the deuterium finally peaks here. This is the most deuterium that we have, continues to create helium, and at some point, the temperature drops where there is no more reactions, and the helium goes flat. The helium is about 1/10, of the hydrogen, and it stays that way. This is stable helium nuclei. The graph goes flat. The deuterium stops interacting because there's not enough energy anymore. So whatever deuterium is left stays, and it stays flat. Okay, it does begin to disintegrate very, very slowly. The helium-3 is also stays flat for a while. This is radioactive. This won't last very long. Here's the hydrogen-3, another isotope of, here we have two protons and one neutron. Here we have two neutrons and one proton. They're both radioactive. They will not last very long. Here's the traces of lithium and beryllium. Okay, beryllium-7 and lithium-6 are radioactive. They will not last very long. They'll be gone in a flash. It's the lithium-3, which is 1/10 billionth of the amount of hydrogen, will last. This is the trace of lithium. This is all that's created in the universe in the first 17 minutes. That's it. We have to wait for fusion. We have to wait for the stars to start creating anything else. Once the stars are formed, 400 million years from now, we're going to go for 400 million years, from 17 minutes to 400 million years, with nothing but hydrogen, helium, and traces of lithium. The rest of the stuff really will go away. The neutrons, yeah, this is something that many people don't know. Neutrons outside of atoms are unstable. They have a half-life of about 6 or 7 minutes. They don't last long, okay? They're looking for a lower energy level. And that lower energy level is where the proton and the electron separates. That the strong force gives it up and allows the proton, which is the most stable baryon in the universe, to exist. And that's why these neutrons just continue to drift down to virtually nothing. There are no loose neutrons in the universe. To the degree that there are loose neutrons, they've been created very, very recently. And they better find a home in a nuclei, or they're not going to last very long. So that's what this graph is. It's very, very readable. And the point is, at this line here, at this temperature here, at this time here, is when the graphs flatten out. And what I want you to see is that the helium grows with the deuterium, just as the reaction we saw, just as the picture, the pretty picture we saw shows. You need the deuterium to create the helium. And once you can't create that anymore, and once the temperature doesn't allow that anymore, the deuterium is no longer eaten up anymore. There's nothing to eat it up. And the helium that we have is what we have. And that's why these three lines flatten out. The other stuff flattens out mostly because they're radioactive and they'll just decay. The neutrons fall off very quickly, 6-minute half-life, and all that's really left are these traces of lithium. Okay, so this is, I think, worth spending the 10 minutes on, because it is one of the most important, besides the cosmic microwave background, which is probably the thing that we learn most about, and most evidence continues to pile up for the overall model. Maybe not inflation necessarily, but the overall model. We believe the overall model is correct. Is the cosmic microwave background? No doubt. That's the second half of this presentation that we're going to go into. This is the other piece. This and the general expansion of the universe of Hubble's law, it really is the evidence of the Big Bang model. Those three pieces: Hubble's law, this thing here, and the cosmic microwave background, and what we can learn from the analyzing it. So what do we have? We have now just an expanding universe of plasma. Okay, it's a plasma still. There are no atoms. It's too hot. It's too hot for any atoms. The electrons can't stay. The ionization energy is much higher. I'm sorry, the energy that's in this plasma is much higher than the ionization energy of both hydrogen and helium. And so the electrons can't stay. They're thrown out of their shells, and we don't have the chemistry that we understand. So this plasma expands and expands and expands, just like the Crab Nebula, okay, is an expansion of this plasma. We know there's a neutron star. I'm sorry, there's a white dwarf star in the middle there. And this will expand and cool until finally we get to recombination and decoupling. Okay? And here we truly are at a place where we understand. We go from the plasma and the scattered photons to finally atoms of hydrogen and helium, and the unimpeded motion of our radiation, our photons. That is the cosmic microwave background. This happens, very, very well-known physics, at 3,000 degrees Kelvin. This is chicken feed compared to what's done at Fermilab and CERN. Okay, this is well understood how this happens to get the creation of stable atoms and the free motion of radiation. Okay, so we now focus. We have 5 minutes left to focus on the cosmic microwave background. What we can learn from this thing. The first thing is that we've learned a lot. There's the Kobe satellite of 1992, where the resolution of the heat map, which is all this is, it's just a heat map, guys, where we had a resolution of 7 degrees. Okay, that was the best that could be done with that technology. Then we have the W map, the Wilkinson's microwave probe of 2003, and finally the Planck mission, where the resolution has gotten better and better. Okay, this is just a temperature map. That's all this is. Okay, the red spots are the hot spots above 2.73 degrees by about 1/100th of a degree. I'm sorry, by 110,000ths of a degree greater, and the blue are the cold spots, and the yellow is something in between. It's simply just a temperature map, is what we're seeing with our eyes. What the radiation is coming at us is black body radiation of different temperatures. What we have to realize is what the theory is going to tell us is that these temperature differences exactly reflect the density differences of matter. That the hot spots are where the matter is more, both dark matter and conventional matter is more concentrated. And those dense spots will remain dense in this picture when it finally comes to the microwave, cosmic microwave background. That density will grow. They're called seeds. They will grow into the stars and the galaxies. And the cool areas, which are less dense, will remain less dense and become more and more less dense as the dense areas become more and more dense, and these will grow into the voids. It's an incredible idea to think that what we're looking at here will grow into the entire universe. The only thing maybe more incredible is that the heat map that we're seeing, the density map that we're seeing, is nothing more, and this is what the theory claims, but understands, what it's trying to justify, is that the heat map that we're seeing, the density map that we're seeing, is nothing more than a blown up picture of the quantum fluctuations of 10 to the minus 36 seconds. Yeah, that's what this is. Inflation spreads it out to the 2.73. It's mostly smooth, but without those fluctuations of the quantum fluctuations, we wouldn't have these density fluctuations, and we wouldn't have any stars and galaxies. That's how continuous this story is. It's quite an amazing theory. Maybe it's hard to swallow, but it is an amazing theory, backed up by all kinds of evidence. I just want to give you a context of what this microwave background, cosmic microwave, is. This is the Planck data set against the real sky. Okay, this is how big this is. Okay, these blotches are big. This is the Chicago skyline, and that's where the sun. That's how big the sun would be, which is a 1/2 degree in diameter. And so that's how big these blotches are in the sky. They're real. If we could see black body radiation of 3 degrees Kelvin, if our eyes could see that, this is what the sky would look like. If we took out the blazing sun and the, and the nearby stars and the cosmic rays, if you could just see the CMB, this is what it looked like in the sky. It's real. Okay, we'll stop here. We'll look at the evidence for the geometry of the universe. All these things, all this evidence is going to come from analyzing the CMB, and that's where we'll end up. We'll finish this off next time, and we'll finish our course. Greg, are there any outstanding questions before we go?
Yes, there's one question from Alan in 7. Is dark matter detectable within the solar system?
No, that is an interesting question. There doesn't seem to be any dark matter in the solar system. It seems that the dark matter in the galaxies are what they call these dark matter halos. they're mostly around the outside of our normal matter galaxies, stars. There's certainly some inside, but it's so thin you can't detect it because there's not enough gravitational lensing. So if it's there, it must be very, very diffuse. But where we see it very easily, because of the rotation curves, right, of the rotation of the galaxies, and the gravitational lensing, where it's clumped is on the outside. And this tells us something about the formation of our galaxies, that the galaxies in this form because they were surrounded by the dark matter, and that's the dark matter helped kind of corral them in. It's not a coincidence that our normal matter is surrounded by these halos. It's because that's how our matter came to be, by hooking on to the dark matter and being helped to coalesce by the dark matter. So it all seems to hold together that the dark matter comes first, and that's why we don't see any strong dark matter within the galaxies too much, and certainly within the solar system, no, not at all, not at all. The coalescing of the planets of the solar system is totally because of the gravitational power of the sun. We don't need any dark matter at all to create that, using the great, nebula hypothesis of the creation of planets. Any other questions?
No, no more questions from me.
No questions. Okay, guys, great. Look forward to the last class. I'll see you then. We will close this thing off and say goodbye.